Hi, welcome back to the meta-heuristic algorithms. This is part one about Cuckoo Search algorithm, and we have another three parts on this algorithm. So, part one will will talk will take you through the Cuckoo Search algorithm, which is a nature-inspired meta-heuristic optimization algorithm, and it can be used for solving optimization problem, engineering design, uh, machine learning, neural network, scheduling, artificial intelligence in general, feature selection in some application, neural network training weight matrix or weight connection of neural network, and many more real-world optimization tasks. So it's based on the broad parasitic behavior of cuckoos combined with the mathematical concept of Lévy flight. Um, why it is called Cuckoo Search? Some cuckoo uh, species lay their eggs in the nest of other host birds, and the host bird may accept the foreign egg or discover and remove it. And this natural behavior extracted from the optimization process. So each Kiko search egg represents a solution. So each egg represents a solution, and better egg will survive. Uh, Poor solutions are uh, neglected or discarded. History of this algorithm, uh, it was coined first time by uh, Shi Yang and uh, Deb in 2009. So by these two people, they have a paper called Kiko Search via Lévy flight, and it became one of the most influential swarm intelligence optimization algorithms. Now, um, they coined this algorithm to have strong exploration, so global search, and it has simplicity because it has fewer parameters and it has better escaping from local minima. And it can be compared with genetic algorithm, particle swarm optimization, and colony optimization SEO. And The performance of CS is excellent. It has good global search and simplicity, and with high efficiency, it performs the task. So Kiko search combines with two concepts. First, uh, broad parasitism. Um, some Kikos uh, lay their eggs in host of others, attempt to replace host eggs, and use survival competition. In optimization, nest means candidate solution, and eggs means new solution. Best nest survives for next generation. Uh, then it has also Lévy flight. Kiko Search uses random walks, heavy tailored probability distributions. This allows small local moves and occasional very large jumps. These jumps help escape from local minima and improves uh, exploration or global search. So there are some original standard uh, Kiko search algorithm, and there are a lot of modifications. So each first rule, I mean, they have some rules. First rule, each Kiko lays one egg at a time and dumps it in a randomly chosen nest. the best nest with high quality eggs carry over to the next iteration or generation. And rule three, the number of available nests is fixed. So it's not like a biological nature of the algorithm is different from the biological by having a fixed size. And there's a host bed discovers uh, alien eggs with probability between 0 and 1. Discovered nests are abandoned and replaced. So this is the if you have a fitness function, this is the fitness function, and you have the update equation whereby next solution equals the current solution plus alpha multiplied by Lévy lambda, and xt is the current solution, xt1 update solution, alpha is step size, and lambda is the random Lévy random flight. Here is Lévy flight equation. It can be found by this equation, and where u equals standard normalization distribution uh, between 0 and variance, and v equals again approximate normal standard distribution between 0 and variance is 1, and beta is 1.5 approximately. So that is the sigma. It can be obtained by this process, by this equation. And here, if this is the tilde, this tilde, it's kind of you can call it the factorial of this value, factorial of this value here. So factorial of this value minus 1. So that is the how you find the variance. Now this is the algorithm: initialize n nest, evaluate, and then find the current best, which is x asterisk, and while stop condition has not met, so you go for each nest and generate Lévy for it, and generate new solution. New solution is equal to this equation, and evaluate whether this solution is fine. If it's fine, accept it. If it's not, leave it. So if x better than x, update the best solution, n4, and then abandon a fraction probability of worst nest, generate a new random nest, end while, and then return the best solution. So these are the steps. So we explained them. Initialize, evaluate, and then generate Lévy flights, update solution, keep better nest, abandon worst nest, and generate new start, a new nest, and it is repeated all the way to here. Now, these are some parameters: step size alpha, and discovery probability is P sub I, and maximum iteration for the algorithm to run, and beta, you have Lévy component. It has not too many parameters. That's the good thing. The advantage explanation about this algorithm is simple, few parameters, strong exploration because it has Lévy flight, improved search. So because of the Lévy, it means that strong exploration, escape local minima, large jump, and efficient, fast convergence, flexible works for many problems. Now, disadvantages: randomness and parameter sensitivity, high exploration. So sometimes it's unstable. You've got alpha and probability affect performance, very sensitive, computational cost, large population may be expensive. If you have a lot of agents, if you have a lot of solutions, a lot of nests, then it could be problematic. So application, they can be used anywhere. Unlimited application for this algorithm can be used. So these are the applications that can be used. And if you compare it with the other algorithm, genetic algorithm, for example, based on evolution crossover, PSO based on particle movements or fish, flocks of fish, ACO and pheromones trial, bat algorithm, uh, echolocation, uh, based on echolocation, the sound of a bat, and Fairfly uh, depends on light attraction, CS Lévy flight exploration. Um, Exploration and versus exploitation. This is local search. This is global search. So Lévy flight exploration and exploitation best nest preservation. So while Lévy flight is powerful, many short moves, few large jumps, and exploration is important in it as well. Avoid premature convergence and escape local minima. This is more or less about this class, and we have the second class about the modified um, uh, Cuckoo Search. So stay tuned for the next class. Thank you.